Electronic components have been a big part of the modern motor vehicle for many years. In this video, we'll look at how they work and how they're used. I'm going to cover diodes, light-emitting diodes or LEDs, photodiodes, capacitors, resistor capacitor or RC circuits, and transistors. This is the schematic symbol for a diode, shown next to the actual diode. A diode is effectively a one-way valve for electricity. It will conduct in one direction and insulate when the current flows in the opposite direction. For a diode to conduct, it requires a forward voltage. In other words, there must be a voltage drop across the diode before it can conduct. This is usually 0.5 to 0.8 volts. I have this meter connected across the diode and this meter connected across the light globe. As I increase the voltage, you'll see that we get a voltage drop across the diode, but not across the light globe, until we reach about half a volt. The diode will now begin to conduct and we get a voltage drop across the light globe. One of the problems with diodes is that when they start to conduct, their resistance drops close to 0 ohms. This means that the diode cannot limit the current flowing through it. If the current exceeds the rating of the diode, then it will overheat and fail. Light-emitting diodes are similar to standard diodes. They will only operate with the current flow in the correct direction, and again require a forward voltage. The LED forward voltage is higher, around 1.1 volts. An LED needs to be connected the right way round to work. The problem we have is that when the LED starts to conduct, its resistance goes down to close to 0 ohms. This means if we increase the voltage, current also increases. And if we increase the voltage too much, the current will reach a point where the LED will fail. We can overcome this by putting a resistor in series with the LED. This is a current limiting resistor. Now if I increase the voltage, the current is limited. And I'm up to just over 17 volts and the LED is working quite happily. This is the circuit diagram for a photodiode. Photodiodes allow current to flow under certain light conditions. They are commonly used as ambient light sensors. Depending on their design and the circuit they are used in, a variation in light levels can be used to suit various applications. Here I have a simple circuit with a photodiode. If I cover the diode over, you can see that the voltage goes down. Exposing the diode to ambient light brings the voltage up. Capacitors are effectively two pieces of metal separated by an insulator. They have the ability to store electricity and then release it again. I've got two sheets of aluminium foil separated by paper and wound up into a tube. Effectively, it's a capacitor. I'll apply a voltage to it. See there, I've got 9 volts. I'll just leave it there for a second or so. When I take the voltage off, you can see that a voltage remains. It won't be there for long, but it actually stored a voltage. They block the flow of DC, but allow AC to pass through. I've got here an AC power supply hooked up to a capacitor. I've got just over 10 volts AC. And if I move to the other side of the capacitor, you'll see that I've got the same AC voltage there. The AC voltage flows through the capacitor. This time I've got 12 volts DC connected to the capacitor. If I move to the other side, you can see there's virtually no voltage. The capacitor is blocking the flow of DC. I have a circuit connected to a capacitor and a bicoloured light-emitting diode, or LED. If I connect the circuit to a battery, the current will flow, lighting the LED green. This will continue until the capacitor is charged. Then the LED will go out, as no more current is flowing in the circuit. If I now disconnect the battery, the capacitor will remain charged. I can now connect the LED across the capacitor, and the stored energy will create a current flow in the opposite direction, lighting the LED red. Capacitors have the ability to release their stored energy very quickly. Here's a 9-volt battery. The negative terminal is connected to an earth clamp, and the positive to a probe. If I connect the earth to a piece of foil, and then touch the probe to the foil, nothing appears to happen. I'll add a capacitor and see what happens. This time we get a spark. And if I add another capacitor, I get a larger spark. Adding a resistor to the capacitor gives us a resistor-capacitor or RC circuit. These can be used for time delay. I have a capacitor and a resistor connected up in series with an LED. If I connect it up to the power supply, the LED operated. There wasn't much of a delay. The delay period can be altered by changing the capacitor value. The same again. I've got a capacitor in series with a resistor to an LED, but the capacitor is much larger. I'll connect it up to the power and we'll have a look at the difference. We can see the charge time changed. There was a delay. It can also be changed by varying the resistance. Same capacitor, but a larger resistor. We'll have a look at the delay this time. As you can see, it's much longer. Transistors can be used as electronic switches. Like relays, they use a very small current to switch a much larger current. Unlike relays, they do not produce voltage spikes when turned off. We'll have a look at two different types of transistors, a PNP and an NPN. The basic difference between the two is the type of voltage used to operate them. One type will use a positive voltage to trigger the switch, and the other will use a negative voltage. Here is a schematic for a PNP transistor. There are three terminals, a collector, an emitter, and a base. It can be seen that there is a positive voltage at the emitter, while the load is connected to the collector and then to ground. The base can be controlled by a switch. The resistor in the base circuit is there to limit the amount of current flowing in the circuit. With the switch closed, a small current flows from the emitter to ground. This small emitter base current flow allows a larger emitter collector current flow. Here's our PNP transistor. The emitter is connected to a 5-volt supply. The collector is connected to a load which goes to ground. We have a current limiting resistor for our LED. The base goes through a switch to ground, another current limiting resistor. When I turn the switch on, the small flow of current in the base circuit allows a larger flow of current in the emitter collector circuit. It doesn't require much current. If I wet my fingers and put it across the switch terminals, you can see the LED comes on. To prevent this, we can put in a pull-up resistor. What that does is it holds the base circuit at 5 volts until the switch is turned on. Put my fingers on it again this time, no false triggering. But if I turn the switch on, the circuit works as it normally should. Here is the schematic for an NPN transistor. Again, there are 3 terminals: a collector, an emitter, and a base. But they are connected differently to the PNP. This time the emitter is connected to ground, and the collector is connected to the load, which in turn is connected to a positive voltage. The base can be controlled by a switch. The resistor in the base circuit is there to limit the amount of current flowing in the circuit. With the switch closed, a small current flows from the base to the emitter. This small base emitter current flow allows a larger collector emitter current flow. This time I've got an NPN transistor. The emitter is connected to ground, and the collector is connected to our load, which goes to 5 volts. There's a current limiting resistor for the LED, a current limiting resistor for the base circuit, which goes to our switch, which goes to 5 volts. Turn the switch on, and the LED comes on. We have the same problem. Very little current is required to operate the circuit. This can be prevented this time by using a pull-down resistor. This now holds the base circuit to ground until the switch is turned on. No more false triggering, but the circuit works as it's supposed to. Turning on an LED is not all that impressive. What else can we use transistors for? In this circuit, we are using an NPN transistor to control a relay in the same way a module would. We've got a 5 volt signal circuit going through the switch into the base circuit. The emitter is connected to ground, and the collector is connected to our load, which is a relay. Turn on the switch, the transistor conducts, and the relay turns on. And just like in a module, we're using a 5 volt reference or 5 volt signal circuit to turn on a 12 volt circuit. Let's measure the current flow in the circuit. I have 2 multimeters connected up to the circuit. Both of them are set to read milliamps. This one is connected into the base circuit of the transistor, and this one is connected into the collector side of the transistor or the relay coil. I'll turn the circuit on. As you can see, I've got 1.25 milliamps switching about 66 milliamps. So the switch in this circuit only has to be able to flow 1.25 milliamps. It in turn turns on the relay, and the relay can now switch a much larger load. That's how a module does it. A small signal operating a larger control that can operate a relay, a component, or whatever. That's a look at some of the electronic components in the modern vehicle. If you are not clear on any section in this video, simply watch it again. Knowing how systems work makes them easier to diagnose. And remember, training is knowledge, the knowledge to give you the edge. Bye for now.